we prove a theorem regarding compact spaces. And first of all, I would like to mention that you can consult the book Introduction to Topology and Modern Analysis, and this book is written by G.F. Simon. So this book is for the students at undergraduate level. So we start the theorem regarding compact spaces. The statement of this theorem is any closed subspace of a compact space is compact. Now we prove this theorem. Let X be a topological space and Y be a closed subspace of X. Closed subspace of X. Since Y is closed, so the open sets of Y, for example OY, has the form Y intersection OX, where OX is an open set in X. So each open set of Y with respect to the topology, you can say tau Y. So OY is an open set in tau Y, and the open sets of Y is of the form OY is equal to Y intersection OX, where OX is an open set in X. So we suppose that the class GI, where I belongs to the indexing set capital I, is an open cover of Y. This class GI, where I belongs to I, each GI is an open set in Y. So this class is an open cover of Y. So we prove that Y is a compact space, and we have to find a finite subcover of this open cover in Y. Since this class, this family or class is an open cover, so by the definition of open cover, Y is equal to union of GI actually they by the definition of open cover, uh, basically we write in this way: Y is a subset of uh, union of GI. I belongs to I. So ultimately after this we can get this equality. So this equality is the consequence of this inclusion. So both are correct, and normally we use this expression for the sake of the simplicity for the students. for the sake of convenience for the students. So it depends upon you. You can write both of them, and means either either expressions are true. There is no any difficulty. Uh, but the expression with the inclusion means y is the subset of union of gi is the basic expression which can be used in the definition of open cover, and this equality is the consequence of the inclusion. Y is a subset of union of gi. So for the simplicity, for the sake of ease, I would like to write in this way, that y is equal to union of gi, I belongs to I. So since y is equal to, here you can write in this way, because this is an open cover, so then y is equal to union of gi, I belongs to I. Now here this is equal to y. Okay, so x, what is x? X is the the union of y and y complement. Okay, so this implies that x is equal to union of gi, I belongs to I. This is equal to y, and union y complement. And note that here, by using uh, this equality, we conclude that the right hand side, this one this right hand side is an open cover for x. So you can write for the memory, that means also you can write here, note that uh, right hand side is an open cover. X. Since X is compact, so this open cover has a finite subcover. Since X is compact, so each open cover has a finite subcover. So ultimately, we deduce that 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 this open cover has a finite subcover. So finite means uh, this open cover uh, this open cover has a finite subcover. Cover means uh, X is the union of finite number of elements of open sets. So this can be written as X is equal to union of gi, where I is from 1 to n, this one. And since y is a subset of x, this implies that we can also write in this way: x is a subset of y is a subset of x, and x is equal to union of gi, I from 1 to n, union y complement. And so this implies that y is a subset of this expression. Here, this y complement has no any element of y because this is the complement of y. So this implies that if we exclude this set yc, this implies that there is no any you can say means it doesn't matter that if we exclude this yc because this has no any element of y. So uh, we still have this expression in this way that y is a subset of union of gi where I is from 1 to n because yc is a complement of y. So we have omit this set. So there is no any means there is no any uh, uh, effect of this inclusion. Okay, means there is no any you can say it doesn't matter that means if we omit yc or not. So the exclusion of yc doesn't affect this inclusion. So we can write this inclusion in this way. We have omit yc, we have deleted yc. So each gi is a subset of y because each gi is open in y. Okay, if we this one each gi is open in y, so each gi is a subset of y. So it means that uh, from g1 to gn all g1 all gi's g1 g2 up to gn, all the sets are the subsets of y. Okay, so each one g1 g2 up to gn, they all are the subsets of y, and their union of gi I from 1 to n is also a subset of y. So this can be written as in this way, and ultimately we have y is equal to union of gi where I is from 1 to n. So each gi is open in y. So this, by using this expression y is equal to g union of gi I from 1 to n, by using this expression we can say that this one is a finite subcover of y. So we can say that we have found a finite subcover of y which is from g1 to gn. This is a finite subcover of y. Hence y is compact space or compact topological space.